So here we go. So now let me know if you don't see the slides, so if you ever lose the audio. Okay, perfect. So indeed the topic is how can we find the interior structure of the planet Earth from earthquake data. So first of all, I'll start with a brief introduction of myself. So I'm Joonas Ilmavirta from the University of Jyväskylä. I did my bachelor's in physics and my master's in theoretical physics and my PhD in mathematics. So you can see the direction of drift over time there. And I'm currently an academic research fellow and associate professor of mathematics at the University of Jyväskylä. So in this flagship, I'm the responsible professor for coordinating teaching and training, but today's talk will have nothing to do with those. We'll be talking about mathematics and some physics instead. Okay, so what I do could be broadly described as geomathematical inverse problems. So from a physical point of view, we measure the shaking of the ground. That is, we have seismometers everywhere on the planet's surface, or at least on the continents. And then that just simply measures the motion of every point on the surface of the planet. And from measurements of that nature, we then want to calculate what is inside the Earth. And that shaking could be initially caused by many different things. So maybe we can shake it ourselves, or we can wait for earthquakes to happen, or there are kind of many things that will excite the Earth, and we'll just listen to what those excitations sound like. Okay, but then from a mathematical point of view, which is what I actually do, is that we, instead of measuring the shaking of the ground, we assume that boundary values to the elastic wave equation are known. So the elastic wave equation is given down towards the bottom of the slide. So it is kind of the simplest version where parameterized by density rho and the stiffness tensor C. So written for the displacement vector field U. Okay, so we assume that some kind of boundary information of the solutions U are known, and we want to prove that knowing this kind of data uniquely determines the material parameters. So this is a very kind of a typical inverse boundary value problem where you want to figure out the coefficients of your PDE from some kind of boundary information. And the overall idea here is that this is certainly pure mathematics. So I aim to prove theorems. I'm not kind of producing anything very tangible in that sense. But this pure mathematical endeavor is guided by relevance instead of elegance. So I don't care how ugly my equations or structures become. I just want them to be of some meaning and of some importance to the physical world. Okay, so so this is kind of in broad strokes what's going to happen. And then we'll start with the first technical idea, which is wave-particle duality. So this is presumably something that you are familiar with from physics, at least on some level. And by waves, I just mean solutions to the wave equation, which in my case here would be the elastic wave equation, but you could have any kind of wave equation and you could still justifiably use the same name. And then particles, to me, are just simple point-like moving objects, whatever those objects somehow physically are. And then from a mathematical point of view, this wave-particle duality means that highly localized waves behave like particles. So if your wave is somehow a very tiny little wave packet, then you could essentially think of it as just a point-like particle, and that point of view is pretty useful. So from a more technical point of view, you could just think of having singularities in your solutions to the elastic wave equation, and you could track the propagation of these singularities by macro-local analysis. But if that doesn't mean anything to you, never mind. But the basic idea is that there is a wave-particle duality, which is kind of perfectly technically sensible and very useful, even on the purely mathematical side of things. Okay, so so in the picture on the left, I have an earthquake. So the earthquake is somewhere in Alaska, apparently, and then these waves then would propagate throughout the Earth. But I can think of these waves as being composed of individual point particles, and these two rays that are drawn in the picture there, these would be two trajectories that these point particles then take. Okay, so these particles travel along these specific kinds of curves, and these curves are determined by the material. So for example, in this picture, as is correctly the case, the speed of sound is higher towards the center of the planet and lower towards the surface, which will cause these rays to curve towards the surface. So they do not go straight, but instead they are curved by whatever the material does. And the particle corresponding to the elastic wave equation is called the phonon. So similarly to the particle of the electromagnetic wave equation, that is the Maxwell equations, that is called the photon, and now here this guy is called the phonon. So with this kind of an idea, we can go from the initial wave data that I had, so I measure something about waves, I can convert that into particle data, and now I know something about the trajectories that the particles travel along. Okay, so then I want to geometrize the picture, and to make sense of the concept of geometrization, I should start with an analogy to something much older, so gravitation and planets. So in Newton's theory of gravitation, the paths of planets are kind of roughly ellipses, and they are caused to be curved by the gravitational pull of the sun. But in Einstein's theory, the planets do not have a curved trajectory. Instead, planets go straight. I mean, they seem to go around the sun, but that actually means going straight. But they go straight in a very specific kind of curved geometry. And then Einstein's theory, that is general theory of relativity, is all about understanding what that curved geometry is like and how it behaves. And now so I assume that is at least on a pop sci level a familiar concept. So now I want to do the exact same thing in seismology with my phonons here. So the old point of view would be that these paths are curved by material variations, as in the picture on the left. But the new point of view that will turn out to be very useful is that I think of these paths as being straight, but in a geometry that is curved in some specific way. So I just declare the trajectories such as the ones on the left to be straight, and I define my geometry that way. So then the material properties inside the Earth that is encoded in a geometric structure, some kind of a manifold. So it turns out to be a Finsler manifold in many cases, but other things can happen. So we originally had our wave data, and we converted it to particle data, and then now we are converting it to geometric data. So the problem is to find a manifold instead of finding the material parameters. So that would be the overall line of reasoning, and then solving those geometric problems is my day-to-day work. Okay, so then a few words about anisotropy, which plays a big role in what I do. So it just basically means that the speed of sound depends on direction. So not just position, but also direction. I mean, in general, anisotropy means that things are not rotation invariant, so that they depend on direction. But now I'm specifically talking about sound in some way. So there are different kinds of waves, pressure waves and shear waves and other things that we need not go into. But then the theorem that I'm stating here, and the only theorem of today, and it's a pretty loose one at that, is that a typical anisotropic medium is uniquely determined by pressure wave travel times. So it is enough to do all your measurements with just pressure waves, and that will be enough information to determine everything you would possibly want to know about your material. And there is unfortunately the word typical there, so this might not hold for all anisotropic media, but most of it, and there are technical reasons for that. But the curious thing here is that this theorem is false for isotropic media. So if you assume that your material is of the simplest possible kind, that it is actually fully isotropic, so it's just the speed of sound or just the two speeds of sound for the pressure and shear waves, then pressure wave measurements will never be enough to determine everything. So you need to measure both kinds of waves. But if your material is less symmetric, so that your model is in some sense worse, then the inverse theorem is stronger and you get this full uniqueness. And the underlying phenomenon here, which may be a bit technical, is that the characteristic variety given by the principal symbol of the elastic wave operator, that becomes algebraically irreducible. And then we can start playing algebraic geometry to explain how this happens and when this happens and so forth. So that is how differential and algebraic geometry end up playing together to save the day. Okay, so then to quickly recap what the basic ideas here are. So I do geomathematics, which is the mathematics of the planet Earth, and so it's kind of driven by applications, but not really kind of directly applied. And that is one of the things that kind of shows that I want to prioritize being relevant over being elegant. But I should also mention that I mentioned the planet Earth, but it's not really necessarily just the planet Earth. So you could do the same thing on many other planets, and we are indeed doing that. So there are things going on regarding, for example, Mars and Jupiter and Saturn, and we can still play similar games. And differential and algebraic geometry, as advertised, make it possible to prove very strong theorems about partial differential equations. So even though kind of at face value, the original physical problem is best understood through differential equations, it turns out that the geometric tools are the strongest ones, and those allow you to make the best conclusions possible. Okay, so this anisotropic thing that you could have, it does make the theory more complicated and might make you unwilling to take it into account, but it actually can make your theorem stronger and it can make your uniqueness results much, much better. Okay, but that's all I had in mind. So thank you everyone. And if you have any questions or comments, I'll be happy to supply more information.